So last time I already explained that I already introduced what is called vector fields, so two-dimensional and three-dimensional vector fields. And the last thing which we discussed was conservative vector fields. So a vector field, because we have encountered a vector field already quite early. So a vector field, for instance, a three-dimensional vector field is a function which maps some space region onto a set of vectors. So you have here three functions p, x, y, z, I plus q, x, y, z, j plus r, x, y, z, k. Those three fields are normally called scalar fields. Now, we have encountered already a special vector field quite early. So when we discussed the so-called gradient field, so we have one special example, namely the special example where the vector field is kind of generated by a function f, so it's given by the gradient of a function f, and f is called the potential function. Now such a vector field, so if you have given a three-dimensional vector field and you can find a function f such that the three-dimensional vector field is a gradient vector field, such a vector field is called conservative. So such a vector field f would be called a conservative vector field. Now vector fields are important in physics. They for instance, appear as force fields. So we saw last time an example, namely, if you look at the force field generated by the gravitation, so the so-called gravitational law, then you have here you have two masses. One of them you place into the origin of the coordinate system. And for every other mass, every other mass is subject to a force, gravitational force, which is described by this vector field here. And we saw last time that this vector field, in fact, is a conservative vector field. And many of the vector fields which are encountered in physics are in fact conservative vector fields. So here a possible potential function would be the function m times g over, and then you have the square root of x squared plus y squared plus z squared. And you see quickly, very quickly that this potential function is really a potential function of this vector field. So we really have that equal to the gradient vector field generated by f. Okay, so this is what we already discussed last time, and the important issue is, from a mathematical point of view, and I guess also from an application point of view. As I said, I cannot tell you too much about applications because I never finished physics. So I do not really understand the applications of this, but I understand what the mathematical meaning of those results which we will discuss are. So at least mathematical, interesting question would be, okay, I give you a three-dimensional vector field or a two-dimensional vector field. Okay, how can you decide whether such a vector field is conservative or not? This would be the first question. The second question is, okay, how to find the potential function. Now this is a problem well understood in mathematics, and in order to solve this problem, we have to introduce a new kind of integral, a so-called line integral. Now, actually, there are many line integrals, so we will learn today at least 4. we start with the easiest one to motivate from a mathematical point of view. So what we have given is, assume we are, because the vector field I just showed you is this three-dimensional vector field. Assume now we are in the plane, not in the space. Okay, so we first consider a smooth space curve, plane curve, sorry. Okay, so you can describe this curve by a vector function. Let's assume the coordinates are given by x of t and y of t, and assume that the range of the parameter is, let's say, between a and b. Okay, so this gives you some curve in the plane. Now, what we want to do is, okay, so we divide the interval ab into n subintervals. So divide AB into n subintervals. Okay, so this will give you points t0, which is a, t1 smaller than t1, smaller than t2, smaller and so on, smaller than tn minus 1, smaller than, and the last one tn, which is equal to b. Okay, and if you plug in those values for the parameters, you will get here corresponding points on the plane curve. So you will have a point, let's say pi, which is given by the coordinates x of ti and y of ti. Okay, so this will give you here some points. So here this point p0. So the starting point, the end point is the point Pn, and then you will have here P1, you will have here point P2, you will have here a point P3, you will have here a point P4, and so on. Now, what we want to do is we want to form the following. First of all, in every of those intervals, we choose a sample point. So choose a sample point in the ith interval. And then the following sum, the sum I from 1 to n. So we have given a function of two variables which associates, so the function is defined on C, okay? And so for every point you have a function value. And what we want to do is, okay, we want to evaluate the function on the curve at the sample point. Okay, so if you, for instance, look at this part here, then you choose a point in between and you evaluate the function at this point, and you multiply this with the arc length of this part here. Okay, so multiply it with the arc length of Si. Now, of course, we have to motivate why are we interested in this. So why do we want to do this? But the motivation is very easy. For instance, if the function f is larger or equal than 0, okay, then you have something like okay. So we plot C in the xy plane. So we have here like this one, and if the function of two variables is larger or equal than 0, what we see is, okay, we have here some, depends on the function. So we have here some kind of fence, okay? And what we are interested in is computing, from a mathematical point of view, what we are interested in is computing the area below the function f. So this here is some function z is equal to f of xy. We are interested in computing the area below the function f and above the curve given by C. Okay. If we do this, then we are an approximation for this area here would be this here. Okay. So it's natural to consider the limit, and the limit will be this area. Or in other ways, we will define the area as the limit. And because this object which you see here doesn't fit in our previous context of the integral, okay, so we will give it a new name, the so-called, so this is a new thing for us, a new object, and we will write the integral over the curve C, okay, along the curve C of f of xy ds. Okay, we have seen this symbol already many times, okay, but it's not related to the previous definition of this symbol. This is a new definition, namely this one. Okay, and this is the so-called line integral of f along C with respect to the arc length. This is one of the line integrals. So maybe a better name, sometimes also used, curve integral, not line integral. This has historical reasons. Okay, so we define the line integral by this limit. And we see that, okay, if f is larger or equal than 0, this has meaning, okay, so it makes sense to look at something like this, to look at the line integral, because if f is larger or equal than 0, the line integral gives you the area of this fence here. Okay, and of course you can use the object. For instance, if you have a density function given, if this is a wire and you have a density function which tells you for every point what is the density, then if you want to compute the mass, you have to use the same approach. You will end up with the same limit. So if you have to compute the mass along such a wire, which is given by a vector function, then you also have to compute the line integral. Okay, so this object makes sense. Now, of course, the first interesting question from a mathematical point of view would be, okay, for which functions f does this object exist? And similar to the usual integral, it can be proved that if f is continuous, this limit will always exist, will not depend on the choice of the sample points. So in this case, the line integral exists. Of f along C, C is defined as once more, so we use this symbol here, f of xy ds is equal to limit n tends to infinity, and then x of some sample point, y at some sample point, okay, now as I said, it can be proved that if f is a continuous function, continuous on C, this is enough to ensure that this limit exists and is independent of the choice of the sample points. Moreover, if f is continuous, of course, as a function of two variables on C, because C is for us the important, is the domain of the function, then there is an easy way to compute the line integral. Namely, you just think about, okay, so you replace x by x of t, y is equal to y of t. So this describes the curve C. So what you do is you integrate from a to b, you plug this in, f of x of t, y of t. And we remember that ds is equal to, if we write everything in with respect to dt, then what we have is the square root of dx over dt plus dy over dt squared dt. So you of course, you have to prove this, okay? It looks like this is trivial, but since we just have defined this object, you have to prove this formally, but the proof is not very complicated. Okay, so this is the definition of the line integral and some comments. Now, what is another comment? So an important comment is that actually the value of the line integral does not depend on the parameterization you choose for c. This is important. So no matter how you choose this function x of t, y of t, and the range of the parameter, if it describes c, then the line integral does not depend on how you choose this parameterization. And so this is the first important remark. The second is if you look at the special curve c, which has y is equal to 0 and x goes from so if you look at the special case, x is equal to t and y is equal to 0 and t goes from a to b, so you just walk on the x-axis from a to b, then the line integral just becomes the ordinary integral. Okay, so that's the first thing. So this is the definition of the line integral for a smooth plane curve c. Smooth means that c as a vector function is differentiable and the derivative not equal to 0. But actually, of course, this definition can easily be extended to the case where c is not necessarily smooth, but piecewise smooth. Piecewise smooth meaning that piecewise smooth c. Okay, so this means that this means you can write c as a union of space curves where the ci are all smooth space curves. Plane curves. Okay, so think about, for instance, something like this here, and then you have something like this here. Okay, so this would be the first C1, C2, C3, C4. All of them are smooth. Okay, but the whole curve is not smooth. It's just piecewise smooth. And we extend the definition of the line integral to piecewise smooth curves as follows. So if C is just piecewise smooth, of course we cannot use this limit definition. So what we say is, okay, in this case, by definition, we just define this object here is the sum of the line integrals over the smooth plane curves which make up C. Okay, and this actually doesn't. It doesn't matter how you write this decomposition. It's independent of how you decompose C into smooth plane curves. Okay, so this is the line integral with respect to the arc length. Okay, and once more, so for this line integral, we have a motivation for looking at it. Okay, the most easiest motivation is if f is larger or equal than 0. This represents here some area. Now we define two further line integrals for which at the beginning we cannot see what the motivation for it is, but in a minute it will become clear that from physics it's important to consider line integrals. Okay, so we define a line integral, so-called line integral, along C with respect to x. Okay, so we write for this line integral the line integral along C of the function f of x, y, and then the ds becomes dx because it's with respect to x. So what is the definition of this? By definition, it's the limit n tends to infinity, sum I from 1 to n. So we look at the similar sum. But the only difference is that for the line integral we defined before, we had here the length of the arc from the point pi minus 1 to pi. Now we just look at the x coordinate. Okay, so now we just look at x of ti minus x of ti minus 1. Okay, or you can write for this delta x. Okay, and similar we have a line integral. Similar line integral. Similar we have a line integral. With respect to y. So for the line integral with respect to y, we write here dy. So this is then a new symbol, and is defined as the limit, where we replace this here by y of ti minus 1. Okay. You should realize that at this stage, defining such two notations, okay, is not very motivated, okay, because we do not have any motivation for looking at this. It doesn't make any sense, this object. Okay. Before we could interpret this as an area, but now there is no real good interpretation of this. Okay. So for us, at the moment, just look at this object as we define some object. Okay. I will show you in a minute why this object is important in physics. And what you have seen certainly in physics is normally we write those two line integrals together. If we have one with respect to x and another one with respect to y, okay, we will write them together, okay, where we have in the integrand, so we have the integral over c, but if the c is the same, and then we have a function dx plus a function dy. Okay, so the definition of this symbol is just you add those two. This line integral, and the corresponding line integral with respect to y. Okay, so meaning that if you have two of them, so you have pxy dx, and you have another one over the same along the same curve qxy dy, we will often use this symbol, so we write them as 1. Okay, so this doesn't mean, okay, if you see this symbol, you say, of course, I can write it like this. This is by definition this rule. Okay, so by definition, this is a new symbol here. This is a shorthand notation for this here. Okay, and the reason why I wrote here P and Q, the same notation I used for a two-dimensional vector field, will become clear in a minute. Because in physics, actually, how the way how something like this arises is you have given a two-dimensional vector field, and you want to compute this here because this has a certain meaning related to work. Okay, but from a mathematical point of view, it's not important for us. For us, we define this object, and then we define this object. That's it. Okay, but so far, no motivation. Okay, for defining this for these three objects. Okay, still, let's do an example. So for instance, this is one example you find in our textbook. So compute this, the value of this line integral, where C1 is the line from -5 -3 to 0, 2, and C2 is the part of x is equal to 4 minus y square, with y is between -3 and 2. Okay. So let's look at the first one, C1. So maybe let's plot it. So here we have x, here we have y. So from this point, x is 0 to 2 to here. Okay, so the first curve is this one. C1. Now, okay, so how do you compute this symbol? Of course, for this line integral with respect to x, if f is continuous, you have a similar rule. So you first parameterize c, and then you plug in here the parameterization, and you replace dx by the derivative with respect to t, dt, and you integrate over the parameter range. So it's the way you would expect it. It's something this is something you have to prove after you define it, but it's not very complicated to prove that you have this rule. So we first need a parameterization of C1, but this is easy. So x is equal to. So actually, if we write it as vector function, then we have this vector here, minus 5, minus 3. And because so the C1 is from this point to this point. So actually, we have also a direction if we talk about curves. So we have this direction here. So we have here 1 minus t, and then plus, and then we have 0, 2 times t. Okay, so this means that x of t is what is minus 5 plus 5t, and y of t is minus 3 plus 3t plus 5t. So so in order to compute this integral, the line integral along C1 y squared dx plus x dy, so what we do is, okay, we integrate. So t goes from 0 to 1. So from 0 to 1, then we replace y squared here by this expression. So minus 3 plus 5t square times dx. But dx is 5 dt plus. Now actually I have to write the dt at the end. Okay. Plus, and x is what? X is minus 5 plus 5t, and dy is also 5. And then everything dt. And if you compute this, you get some value, minus 5 over 6. Okay, you see that the computation of such a line integral is also not very complicated. Now, how about the second line? So the second line is a parabola. So if x is equal to 0, you are here and here. So you easily see that the second one is is a curve like this here. So this is C2 here. In particular, you have the same starting point and the same end point. Okay. If we compute the line integral, you can do this on your own. It's not very complicated. For the second one, then what you get is something different. Okay, so our hope that such a line integral can be computed easily for a given curve by just evaluating our hope that this line integral just depends on the initial and end point, okay, is not satisfied for this example here. But we will one other main question. So one question I already showed you. So one question which we want to solve is, given a vector field, okay, how to find out that such a vector field is a conservative vector field. Another question is for which functions here is this line integral independent of the path you choose, and just depends on the two on the values of the two endpoints. So meaning that if you walk from this point to this point like this or like this, it should be the same result. So we want to also figure out for which functions here have this property that no matter how you go from one point to the other, the line integral will not depend on the curve you choose. So here you see an example where this is not the case. So for those two functions, okay, the line integral will indeed will depend on which path you choose. Okay, so any questions? Any questions so far? Okay, now before I want to go on and before I want to discuss a more easy way, because sometimes computing the line integral just by using this definition might be rather complicated, but there is a very easy way to do it. Namely, there is a relation between line integrals and double integrals. But before I do this, I just want to spend a few minutes to explain why this object is important. Okay, because we haven't given any motivation yet for this object. Sometimes in mathematics it's not so important to have a motivation. Okay, you define something, you want to study its properties. But since you are not mathematics students, maybe this is not enough for you, just to look at this object and say, okay, what are the properties? So for this, assume we have given a two-dimensional vector field. Which describes a force, so a force field. And assume that this vector field is continuous, which means those two guys are continuous. Okay, and assume you have a smooth space curve. Say space curve, plane curve. Okay, so you have here, again, we have a curve C. And for every point here, we have attached a force given by the force field. Okay. Now, a question you might be interested in physics is, okay, what is, how to compute the work if this force field is moving a particle from here to here. Okay. So how to compute the work done by F in moving particle along C. Okay, so for this, in order to solve this, so again we say that we have given a parametrization of the plane curve where t is between a and b. Okay, we walk in this direction. So we move the particle from here to here. Now, in order to solve this question, the first thing you want to do is you approximate it. Okay, so because we know that if this curve would be a line, okay, it would be easy to compute. So what we do is we divide the interval AB into n into n subintervals. So divide AB into subintervals and choose a sample point in every subinterval as before. Okay, so you have some ti star which is in the i's subinterval. Now you can approximate the work which is done on the. So you will have here, let's say, a subinterval from pi to from pi minus 1 to pi. This part here of the curve. Okay. So for this part of the curve, you can approximate the work as follows. So you look at the force at this sample point. So you have the force at x of ti par, y of ti par, and z of ti par. Sorry, I have only 2 coordinates. And you multiply it with what? You multiply it scalar multiplication. That's the way we compute the force, as we know, with the tangent vector to C at this sample point here, multiplied with the length of the arc. Okay, so you multiply this with the tangent vector at the sample point times the length of the arc. And this is scalar multiplication because these are 2 vectors here. Okay, so that's the way you can compute the force, the work which is done by the vector field in moving the particle from here to here. And now what you do is, okay, you sum over all of them, and you let n tend to infinity. Okay, and what you get is the work. Okay, so you see that that indeed the work is given by the line integral, because this was our definition of the line integral. Of what? Of the line integral along C of the force field times the tangent vector ds. Okay, so the work is given by the line integral over C, and then you have the force field scalar multiplication with t, so the unit tangent vector of the curve C ds. Okay, so you see here in this context, you see already that okay, we can use the line integral, but not with respect to x or with respect to y. So the first line integral which we defined with respect to the arc length in order to find the work. Okay, so this still doesn't motivate why do I look at the line integral with respect to x, the line integral with respect to y, and why do I merge them? Okay, you will see this in a minute. So, but for this integral, okay, in physics normally we write this is their own. This is another line integral, the line integral of a vector field. Okay, so in physics normally we make the definition that they write for this f, then scalar multiplication with dr, where r is the vector function describing the space curve. So this is just another definition, another line integral, the line integral along C of a vector field. But this is how the line integral of a vector field is related to the line integral with respect to the arc length. Okay, and how is this related to the line integral with respect to x and with respect to y? So for this, we recall that the tangent vector is given by the derivative of the vector function describing the plane curve over the length. Okay, but we know that ds over dt is also the length of the derivative. Okay, so we plug this in. We plug this in, and what do we get? So the line integral along C of our vector field dr is equal to because we need some parameterization, so let's say the t goes from a to b. So by plugging this in, this becomes a to b, and then the vector field evaluated at x of t, y of t, multiplied with the derivative of the vector function over the length of the derivative times the length of the derivative times dt. Okay, now those two here cancel, everything becomes what? The integral from a to b. This here is the dot product. Okay, and so if we use our function p and q in order to describe here the vector field, what we have is p of x of t, y of t, first coordinate multiplied with the derivative of this one because of dot product, plus and the second coordinate of this vector is this one, so q of x of t, y of t, multiplied with the second coordinate of this one, which is the derivative dt. Okay, now we realize this here is exactly the line integral along C of p of xy dx plus q of xy dy. So this gives us the relationship between the line integral of a vector field and this object which we have defined and which up to now didn't make any sense. Okay, so I first defined this object without giving any motivation, then this object, and then this new object. But here we see what the motivation is coming from physics, namely if you have given a force field and you know the component functions. Okay, if you want to compute the work done by this force field in moving a particle along the curve C, then what you have to compute is this line integral here. Okay, so I guess everything is familiar from physics. It's just a different way of looking at it. So you see, actually, these kind of things are not so deep. Okay, you just have to define them once. Okay, and then it's not so complicated to use them. Okay, so any questions so far? Okay, so just to summarize, we have defined now 4 line integrals. Okay? One is with respect to the arc length. So this one with respect to the arc length. One is with respect to x. One is with respect to y, and the final one is with respect is the line integral of a vector field. And here you see how all those are interrelated from a physical point of view. Actually, there is only one which is important for us, namely, and for this I have to explain a little bit. So normally if I have given a plane curve, okay, with the plane curve also comes the orientation, okay. The parametrization is not important, but the orientation is also important, okay. So the way, if you have given something like this here, a plane curve, whether you go from here to here or from here to here, this is important. Okay, so normally with C, C normally is something like this, and the orientation. Okay, but the parametrization doesn't matter. Now, if I write minus C, I mean the same plane curve, but the orientation is reversed. Okay, so of course, if you do this, if you reverse the orientation and you look at the line integral with respect to x, then how will this be related to the line integral along C of f? You will have a minus here, because in the definition you have you multiply with the delta x, but this will reverse. Okay, so you have this here, you have this property, and you have the same if you have the line integral with respect to y. But if I do the same with the arc length, if I replace here x by s, okay, no minus, because the arc length doesn't have a sign, okay. And if I, so maybe I should write also this. So here the orientation of the curve does not matter, and for the line integral of a vector field. Again, you figure easily out that the orientation indeed matters. so these are the properties. Of course, there are more, but these are the properties which we will need in the sequel. Now, we need some notation for a plane curve. So a plane curve is called closed. Okay, if you closed should be clear, so you go once around. Okay, so if the initial point and the end point are the same, okay, this is closed. What is more important is simple. So C is called simple. If it doesn't cross itself. Okay, so if you have something like this here, would be not simple. Where this one is simple. Now, you certainly know from physics that if you have a given line integral, where C is closed, then normally we emphasize this by adding here this kind of ring. Okay, so this is for the case where C is closed. So in this case we have this notation here. We just have a ring around. Okay, so we wanna figure out how to. For instance, such a line integral can be quite complicated. I give you one. For instance, this one, if you ask to, we are going around the circle, and we have 3y minus e to the dx plus 7x plus dy. Okay, if you try to first parameterize the plane curve, plug in the parameterization, you will encounter a quite complicated integral to solve. Okay, so solving this, computing this line integral will not be very easy because of the complicated nature of the functions. Okay, but fortunately there is a much better way, because there is a result you have certainly learned in physics, so-called Green's theorem, which tells you how to go from a line integral, which tells you the relationship between a line integral and a double integral. Okay, so before I state the theorem, I need one more notation, namely the orientation of a space curve. So normally the orientation which we choose is okay. So if you have given a closed simple space curve C, okay, then let's say without any orientation. Now we will identify two orientations, positive and negative. Okay, so one of the orientations, because we have two ways, we have two possible ways. One will be called positive, one will be called negative. Now, what is the definition? So positive is the positive orientation is if you walk on C, okay, and because C will enclose, if C is closed, C will enclose some plane region. Okay. Now, the way we define positive is if you stretch out your left hand, okay, then the left hand will point inside the will point towards the region which is enclosed by the plane curve. Okay, so if you walk here, okay, if you walk around and stretch out your left hand, okay, then you have to walk in this direction such that your left hand is always directed to the region which is enclosed by the plane curve. Okay, and this will be called positive, and the other direction will be called negative. Okay, so this is positive. Positive oriented. Now Green's theorem, which is a quite deep result. Tells us the following. So assume that C is positive oriented closed, simple, piecewise smooth. Like this here. Here you see this would be positive oriented with this orientation here. If I walk just once around, simple, closed, and piecewise smooth. Okay. Then assume you have given a two-dimensional vector field. That f of x y is equal to pxy I plus qxy j has continuous second order continuous partial derivatives, which means p and q. So the scalar fields have continuous partial derivatives. Then, if you want to compute the curve integral over C of the vector field. So I could also write this in vector notation, but I write this in this notation. So this is the, in terms of physics, this gives you the work by moving the particle around C. Okay, if the particle is moved by the force field, which is given by this vector field. Now you can compute this by the double integral. So the region which is enclosed by C is called D, so by the double integral, and then you have the partial derivative of Q with respect to X minus the partial derivative of P with respect to Y dA. Okay, so there's a relation between the line integral and the double integral. And this relation is given by Green's theorem. Actually, proving Green's theorem is not easy. It's easy to prove if you make additional assumptions for D. Okay, but under this general setting, it's quite complicated to prove. In our textbook, you find a proof where we have some additional assumption for D. Okay, but the general theorem is not easy to prove. Now, I guess you have certainly seen this in physics, and you also know how to apply it. You see this obviously. This obviously has some advantages if you want to compute here this complicated line integral, because okay, you have to take here the partial derivative of Q with respect to X, and this complicated part will disappear. And here you have to compute the partial derivative of P with respect to Y, which means this complicated function here will disappear, and then everything will get very easy to compute. So you see, one advantage of Green's theorem is, okay, it helps you to for some complicated line integrals. Okay, sometimes, but not necessarily always, the double integral is more easy. Now, what is for me more important from a mathematic point of view? What is the meaning of this theorem? Because it's quite interesting. From a mathematic point of view, what you see here is one version of the fundamental theorem of calculus for double integrals. Okay, that's the way I see Green's theorem. Okay, so this is like the fundamental theorem of calculus we learned last semester. Okay, how to see this? If you have if you look at one version, or let's maybe call this okay, so one version of the fundamental theorem of calculus tells you, okay, that this is given by f of b minus f of a. Okay, so you have given this function. You have given the derivative of f, which is here the integrand. You want to compute this integral, and how do you do it? Okay, the integral just depends on the two. So you have this interval here, the interval from a to b. So this is kind of this is the domain over which you integrate. Okay, and the fundamental theorem of calculus tells you, okay, the only thing which is important is this point and this point, the two boundary points. Okay. Now this is the same for double integrals. Here you see you have a double integral. This is kind of you can look at this as a derivative of some function. Okay, and this tells you that okay, so this d here involves here the whole domain. Okay, and this tells you that you can express the double integral. Okay, that you can compute the double integral. Okay, just by looking at the boundary. Okay. So you can evaluate the double integral by looking at the boundary. It's a little bit. This of course is more complicated than this here. Okay, but so if we would have asked ourselves, okay, is there a version of the fundamental theorem of calculus for double integrals? Yes, there is one. This one. But for this you have to introduce the line integral in order to express it. So you see, from a mathematical point of view, the interesting thing is this here can be considered as the fundamental theorem of calculus as one version of the fundamental theorem of calculus for double integrals. Okay. Sometimes, actually, Green's theorem can also be used in order to compute double integrals. Okay. Sometimes the double integral is more complicated than the line integral. For instance, you can also use Green's theorem in order to compute, let's say, areas. Okay, so how do you do this? You just choose a q and a p such that this here becomes 1. Okay, then the meaning of this here is the area of D. Okay, and you have several possible choices for q and p. For instance, you choose q be equal to x and p be equal to 0. This is one possibility. Or you choose p be equal to minus y. Okay, so you can express an area by double integral. So you see that the area of D is equal to, okay, so let's, for instance, Q is equal to X. Then you see it's the line integral over C, where C is the boundary of D. We sometimes use this symbol here, so the boundary of D. And then you choose Q to be equal to X, so you have X dy. Or another way is minus the line integral. So another way would be you choose p is equal to minus y. So you have y dx. Or yet another way is you can write this as 1/2 and then the line integral. For instance, you choose now x minus y. I have to write this difference. X dy minus y dx. Okay, so you see it would be another way. And for instance, how is this helpful? So sometimes things are more easy to compute by using a line integral. An example would be, for instance, the area of the ellipse. Compute the area of the ellipse. square over a square plus y square over b square is equal to 1. I should say the area enclosed by the ellipse. Sorry. Okay, so you can use Green's theorem in order to express the area for instance, you can choose this form here, 1/2, and then the boundary of d, and then you have x dy minus y dx. Now you have to choose a parametrization in order to compute this of the ellipse, of the boundary. The parametrization you can choose is x is equal to a times, for instance, cosine of theta, and y is equal to b times sine of theta. Okay, where theta goes from 0 to 2 pi. So you see that, we need x and dy, so dx is equal to minus a times sine of theta, d theta, and dy is equal to p times cosine of theta. Okay, so you see that this becomes here 1/2. And then you integrate from 0 to 2 pi. And if you plug in this x here, x dy is a times b times cosine square of theta plus, and for this part you have the same, a times b times, but sine square of theta. Okay, so you see that's equal to a times p times pi, so it becomes very easy. Okay, so this is another way you can apply Green's theorem. Actually, Green's theorem also holds in a more general setting, also holds for plane regions which have holes. So for instance, if you have a hole, because the original version didn't for such a plane region. D. Now, what you have to do is you have to again you have to first to orientate the boundary. Okay, so here if you look at this boundary, okay, we have to walk like this. That is positive oriented. Okay, but here the other direction. Okay, because again of the left hand rule. Okay, you walk, you stretch out the left hand, and it has to point towards D. Okay, so here this boundary you will orient like this here, the other one like this here. Now you cannot immediately apply Green's theorem, but what you can do is you can slice it here and here. Okay, and then you get two plane regions, D1 and D2. And for the first one, you walk like this here, and you walk here, and you go here, and you walk here. And for the other one, you walk like this here, and here you go in the other direction. And then you walk around this piece here, and then you walk like this here. Okay, so you see that if you look at the double integral over D, and then the partial derivative of q with respect to x minus the partial derivative of p with respect to y dA. Okay, because of the properties of the double integral, you can write this as the double integral over D1, and then the double integral over D2 . And now for both parts, you can apply Green's theorem. Okay, you see that for D1, okay, if we walk like this here, okay, the plane region is always to the left. If we stretch out the left hand, it points towards D1. So what we get is, okay, the first part is the line integral over C1 this, okay, over C1, and then you have P of xy dx plus Q of xy dy. Okay, and the second one is the line integral over C2 of P of xy dx plus Q of xy dy. And you see that because of the properties of the line integral, if you walk from here to here, and then you walk from here to here, those two will cancel. Okay, because one of them is positive, the other one is negative. Okay, so you see you can merge those two, and what you get is so this should come here. So what you get then is this is the line integral not closed anymore over C P of xy dx plus Q of xy dy. So actually you can extend Green's theorem to the situation where the plane region has a hole. Okay, next time we will see that Green's theorem is helpful in order to answer the question which of the how can I see that the given two-dimensional vector field is conservative. So more or less Green's theorem will provide an answer to this question.